All right, so I really didn't sleep enough last night. I was a naughty speaker, so I might be slightly incoherent, so my apologies. Sane may or may not apply anymore. But basically, parsing for the moment in computer science is mostly, for most people in most problems, they think of it as a pretty straightforward process. You deal with an LLR grammar, you deal with LR grammar, something like that. You have a parser generator, something along those lines, parser combinators, and then you write what amounts to a recursive descent parser or something that conceptually works like that and parse your data. The problem is we're working in a perverse environment, APL in this particular case, and we have to write a parser for APL, which there are no extant, successful, offline, static, commercial grade parsers for APL, including for all the commercial APL implementations. They don't parse like this. They don't make a parser available. And internally, they don't use a parser because it's a difficult problem, because APL is not well specified. And in our case, we can't design this system because we can't use traditional like black box reference implementations because the interpreters are themselves known to be buggy in certain cases that would matter for using it as a reference implementation. So there's no ground truth for an APL parser. So we have to iteratively build this up. And this middle section here, that's the problems we run into internally in the language, right? We're dealing with a mixture of dynamic and lexical scope. We're dealing with dynamically typed language, but its parser, it depends on the types of the expressions, and variables in particular. And there's extensive use of eval all around. Often we will encounter highly connected call graphs. Syntax errors don't necessarily happen at compile time. So sometimes we need to push a syntax error to the runtime. And we have to have control over when we do that. We want to give nice, good error messages under those conditions, right? And sometimes that means we need context that may or may not seem to exist. The problem with having a highly connected call graph of a parser that is ambiguous or parameterized over the types of your system is that some of those types may be defined way apart from where it was used, which means that potentially we need the whole program source in order to parse an expression, right? In order to derive enough information. So, and there are forward references in these documents that we have to account for. And we're needing this to parse very large code bases, so it has to be efficient. And because it's part of the Co-dfns project, it's part of the whole goal here is to have a self-hosting compiler that runs on the GPU and hosts itself in a data parallel fashion, which means we have to make this parser work on the GPU as well, and there aren't a lot of developers on it. And some of our code bases that we actually have to parse, some of our first targets are in the millions of lines of APL code that we have to parse, and that all has to be done in memory, and it has to be fast enough that single machines can do it reasonably well. So it's not a very fun place to be if you just want to use your Antler parser, right? So what we've done is essentially developed the extension of the work in the rest of the Co-dfns architecture and applied it to parsing, calling it nano-parsing. And it's GPU compatible, and importantly, it has some really nice features. One of those is it decouples error reporting from the actual parsing recognition. So those two things can be thought of as orthogonal entities. And at any point in the parser, we can perform arbitrary computation. This is important because now we can do whatever we want, whenever we want inside of the parser with full access to the entire state of the parsing context and no worries about local myopia, right? And because of the design, it's well suited for execution on an interpreted environment as well as a compiled environment. So it will run on things like the Dyalog interpreter efficiently and performantly, as well as on a compiled environment, which you don't always get in a normal parser because interpreter overheads can undermine your performance on a parser if your read costs are too high or your abstractions are too high for a given node or something like this. And because of the way it's designed, it's much easier to introspect at scale to see what's happening, what's being done. And because of the dependency arrangements, it's very easy to see what code is and is not going to be impacted by a given change. And it's a much more regular way to look at it. And it's very easy to add and modify different passes that you need. So, thus endeth the slides, right? So now I figured the only way you're going to get a feel for this is to really experience what we're dealing with here, okay? And so the rest of this is hopefully my attempt to embody the experience that we were running away from and that we're trying to go towards, right? So this is not a talk where you're expected to understand all the APL. So instead of trying to understand all the APL, understand the pain and the joy and the features and the capabilities that we have in the use of the APL that we're working with. So what did we start with, right, in version 3 of the compiler? This, all you computer scientists should immediately know what this is. Because obviously, it's a meta-programmed PEG parsing system where all those underscored objects are just parser combinators for a PEG parser generator, or a PEG parsing system. And here is meta-programming, which you can do in APL, which is this PEG macro. I'm calling it a macro. It's not. But I'm not going to tell you why it's not. So what we do with that is we have things like a tokenizer. And this lets us write our tokenizer the way you would typically expect with like BNF productions. Right? And for a tokenizer, it seems to work just fine, right? Things like digits and brackets and semicolons and alphanumeric characters and everything like that. But then, unfortunately, we get to the parser. And you can see we have PEG for most of it, right? But we start to run into a problem where the PEG system is not expressive enough to encode what we actually need to do. And obviously, the first thing we do is we have to find a way to couple node creation with the parser recognition. That in and of itself introduces an indirection that results in lower performance. And then, let's say we have to make a change to this thing. Well, because we have to do type inference throughout this whole piece, we had to thread an environment through and try to do sufficient type inference inside of the PEG system and thread that state through the system to get it where it needed to go, which meant that we have things like this sitting around, which its only job is essentially to do what amounts to function specialization and propagating various types of environments through various functions. But it's not quite enough to do what we needed to do. And PEG wasn't quite enough to do what we needed to do. So sometimes we had to write functions that weren't in the PEG syntax to get around the fact that we had no way of easily expressing what we wanted in the PEG syntax. So now to read this parser, you actually have to be in 2 different modes. And then let's say we want to make a change. You've got parenthesized expressions. And we can see where it's used in certain places, right? So far, it's only one forward reference, which seems fine. But then we've got expressions, and those are used in a bunch of places. And more importantly, they're scattered all throughout this whole place, and this is recursive, right? So all of these references have these dependencies all over the place with cycles everywhere. And atom is another version. Like atom, the very concept of an atomic thing that we're parsing as an object, depends on unit, which depends on parenthesized expressions, which depends on expressions, which depend on, and it's this giant cycle. And so to understand how this is actually working, it starts to get to be a headache. And now, what if I wanted to put a stop somewhere in here and see how the parser is going, right, and debug it? What if I wanted to see the state? What if I want to control my error messages? There's no way of easily saying, well, if I get this, but I don't get this, and I have this somewhere here, and this happens here, I really want this kind of error message, but if I don't do that, I actually want to do this, and sometimes I want to highlight all of the things that went wrong, all as a bulk, and sometimes I only want to highlight one. You don't have any of that control in this space, and you don't get to control when you give your error messages either, right? You've lost everything, and so everything gets confusing. So what is our solution? And this is, once you know the solution, you can go use it, you're done, right? So all we have, the tokenizer is written in this way, but we're going to focus on the parser, right? So conceptually, all we do is we start by assuming we have a forest of single element trees that is the original sequence of our parse string, right? And that tree, now, we're just going to apply tons of little tiny parser passes to that tree, refining it so that every time we refine it, the tree becomes a little bit closer to the final result that we want. And the way that we think about this is if you imagine a BNF, you've got these dependencies. Some things are more important than other things. So there's actually like a semi-lattice of dependencies and interdependencies between various concepts that you want to parse. So the first things, in this case, is strings and comments, right? You want to make sure you get strings and comments out of the way, because if you don't have strings and comments out of the way, you might be parsing as code something that actually belongs in a string, and you might be parsing as a comment something that actually is inside of a string, and so forth. So that's sort of the first thing that we often have to do. And that's actually handled back in the tokenizer, which actually, do I have that easily available? So we get our basic character classes, lines, and comments and strings, right? So in a normal recursive setup, these things would kind of bounce back and forth on the stack, dealing things, or they'd take a branch somewhere early in your thing. Because this is just one pass, followed by another pass, followed by another pass, followed by another pass, all the way down until you're done, one of the main tricks you have to do here is you have to find a way to take things that are recursively dependent and split them into multiple little passes that progressively refine the idea until you're done. And so that's actually what we end up doing in something like the comments. So we actually split comment parsing and string parsing into these multiple little phases. And you don't have to read the code, you can just read the English parts, right? And that's the architecture. So we say, get rid of all the other stuff, get rid of the recursion, and just write your parser top to bottom as a giant string or a giant train of just one function after another. It's one function doing one pass to the next pass to the next pass. All the flow of the data goes from the top to the bottom in one direction. And you are allowed to introduce fixed point iterations in the middle at the top level. So sometimes you might have to refine something over time. So you're allowed to sort of jump back as long as it's at the top level, not internally in the pieces. So individual passes can be repeated to a fixed point or some other condition. But other than that, everything just flows straight down. So how does this actually work, and what are the benefits that we get from playing with this? So I have a sample source program here. And it's actually a fairly sophisticated APL program. I tested it beforehand. I think this is, I don't want you to worry too much about the code. It's better to see the shape of things to come, and you'll see more of the shape if you keep it at this font size. So don't worry about reading the specific code. It's just we've got some code that's like got a couple of functions in it, right? So it's basically one function that contains another function inside of it. So let's see if I have done this correctly. We have a stop in our debugger at the end of the parser and at the function specialization part, and then also at the beginning. So what I can do is I can now just run the parser after the tokenizer on the source code, and we'll get a stop inside of the beginning of our parsing, right? And now what we can do is we can actually see, we can pretty print the tree. Oops, helps if I don't double tick. And so this is the initial state coming from the tokenizer. And this is the entire state right now. And so you can see it's very flat. In the tokenizer, we actually do a little bit of parsing because there's context that we need in order to do tokenization the way we want. So we do a little bit of that in the tokenizer before we get to the main parser. And we have this type variable. So we have the parent vector, a type, a kind, value data, which is in a symbol table. So these are symbols that reference a symbol table, right, which is these symbols here. So if I took these symbols and mapped the symbol table, you would see all of the symbols that appear inside of our tree, as it were. And we have position data to tell us what the range in the original source was. But we're not really going to use any of this except for PT, K, and N, right, which is our main structures. These are the fields of our structs that we're working with conceptually. So I can say something like, what are the types of all the nodes? And then I can say, well, now let's visualize those out. And we can see what we've tagged as the types of our nodes so far, right? So we can see we've got some Z nodes, some K nodes, variables, primitives, character nodes. And so all of these are just the classes that we've refined so far. But we can then just keep going, right? So we can start executing. We just executed, computed some name classes. Now what we did is this one, we're going to nest. This is our first sort of nesting pass. We're going to take those, and we're going to wrap our top-level points in these extra Z nodes. So now what we've done is we've sort of taken the Z nodes that were at the top level and created our first top-level piece up there at the above. And then we'll keep going. Now, in these function bodies, right, you'll see we have these Z nodes here. Those represent sort of delimiters for our lines. And so we're going to take each line and parse it individually. And so this is sort of, now we have to parse the lines up. And that's what wrapping all function expression bodies as Z nodes is going to do for us. So we're going to take a look at that. And now you can see we've parsed up these lines into the individual statements that we have, right? And interestingly, if we look at this and we visualize the subkinds with these, most of the subkinds are 0 right now, because we don't have a lot of data about the subtype of each of these classes of nodes. And we're going to refine that K field over time so that we get more differentiated ideas of what each of these pieces are as we go through. And so we can just keep going, and now we don't have any trad funds, so we can completely skip all of that stuff, thank goodness. And now we can look for like empty Z nodes. So you'll notice in here, we have like these Z nodes that don't do anything. Well, there's nothing to parse inside of those, so we might as well get rid of them. So we do something like that, and then when we print it out again, you'll see that the Z nodes that were there are gone, and I like to have a little bit clearer visualization, so I don't need the K for the moment, so we'll get rid of that. And you can see sort of how we're going through this. And then we want to take those Z nodes at the top and start parsing our main namespace. So we have to parse the syntax for the namespace, make sure that's all good. And you'll notice that one of our Z nodes and our Z node at the tail has now wrapped all of this into a single namespace node, single module. And now we've got if statements. So we're going to go through there, parse those. And you'll notice now we have 2 of these if statements that have been introduced into our parser here and here, right? And it keeps going like this. Pretty standard stuff. Parsing brackets. Now we parsed brackets and we did something most people would consider very bad, right? So if I run the same program again, it's going to give me an error. Why? Well, because there's a concept that's a very transient concept that we don't care about, we don't want to sit around, and we don't want it to take up mental space in the source code anywhere else. So we don't give it a name. And if you paid very close attention, you'll notice we said parse brackets and parentheses into neg1 and Z nodes. So specifically, the concept of a bracket, we don't want to reify that by giving it an actual type name. So we give it -1. So that doesn't stop us, though, because we can just get rid of that and still print it. And now you'll see those little dots there and there. Those are our bracket nodes that we have to deal with, the opening and closing bracket nodes. So we keep going through here. Convert, we don't use any of those. We're going to go through these. And we start doing something. And so far, all of this you theoretically could have done in a peg parser pretty straightforwardly, right? However, this is all data parallel in its semantics, right? So this is GPU compatible as far as execution goes. And now we have this first part. We have to have some way of managing lexical scope right now, because we have to we have to connect a variable reference to its lexical scope. So this is the first part where we start having to introduce concepts that are easier to express if you have full computing power. And so we start marking which nodes are reasonably possible to be bound. And then we go through and we start looking for empty bindings. And notice this is one of our first places where we completely decouple the error from the parse. And so we check at this point for empty bindings, because this is a good place to verify a certain invariant that we want for all of the code below it. And we can check that an error if we don't have that, and deliver an error message to the user about this and give some useful feedback. Right? And if somebody wants to see what the errors look like, they're nice and pretty, they underline, and they're all good and fancy, but this is totally decoupled from actually doing the binding in lexical scope itself. And we can keep going. And now we introduce another field, and both VB and BM, those are 2 variables we introduced here, right here. Those are just temporary fields that we introduce to our struct that are used internally and then discarded, right? So one of the benefits of this architecture is we don't have to worry about our type signatures going crazy, because our type signatures, we don't have them. And we make them work implicitly rather than having to track that stuff. So we don't have to mark a change in type of our data structures at this point. We just add some extra stuff and get rid of it when we no longer need it. And we're going to do a little thing. And now here, we have this first fixed point thing that we're going to do, and we're going to go over all of these binding nodes, and we're going to wrap up all the bindings and split them into the thing that you're going to bind to and the thing that is the value that you're going to bind. And we do that, and then once we visualize that, you'll see we've made some progress, and we have these binding nodes, these B nodes, sitting around everywhere now. And these Z nodes serve as our sort of markers of things that we're still working on parsing. So they're grouping nodes that allow us to track where we are in the parsing state. right? So we keep going, la-di-da-di-da, do-do-do, and we do things like computing the frame bindings, the local scope. Now we start, linking them all together. We start making closures, and now we run into one of our first big, scary behemoths, which is now that we have all this, we can't actually do the type inference until we've specialized our types. So we have to generate a specialized function for all that, and then we run into a problem with our display. We've got a ton of type specialization, right? And that's no fun, and so what we can do is, if we want to continue to visualize this stuff, let's go to my cheat code just so I don't have to type it. Where is my cheat code? Oh, do I not allow myself a cheat code? Yes, I do. We'll just, Actually, I think I didn't give myself my cheat codes. See, what? I just might, actually, but no, I'm going to open. No, okay, so we'll do it by hand anyways. So we want to simplify this down, right? So one of the ways that we do that is we will sometimes just display the data in a different format. So we will do a 0, max t, and look at the k values. And in this case, maybe we want to look at the, well, that's good enough for now. So we'll transpose that. And right, k, type p, and I want p here. Yeah, and yeah, okay. Wait, that is, oh, whoops. I could commute that, there we go. So oftentimes when I'm working with a tree, I won't visualize it. I'll just work off of this table structure to look at everything. And it actually clearly is. But let's say we don't actually want to do that. So maybe we only want to look at some subtrees of the thing. So let's start with that. So let's mask off. We want to continue to keep the root node. And then what I'm going to do is the function specialization introduces a lot of specialized functions that basically are the same thing. So I'm going to say, if you're one of the nodes of a closure, and you are the last function member of where the nodes with type equals f. So I'm looking for the functions, the nodes that are functions. I'm looking for their parents, and that allows me to use the first occurrence flipped, not transposed, flipped to get the last child, or the last sibling of the piece. And what this will do is give me mask p not equal and control C length error. That's what I get. Let's go back here. Yeah, okay, so let's tally p, tally mask. Oh, duh. I want this to be a mask. There we go. That'll be better. And then, so I'm looking for, basically I'm looking for the function nodes, and I'm looking to grab, I want just the function nodes and grab the parents, and it has to be ANDed with this and this and this and the p node. That should give us, so the first mask, t equals f, this gives us a Boolean vector, and I can then filter that by p. I forgot to expand it. There we go, okay. So now this is a mask of all the nodes we want to keep alive, right? And if I want to visualize how I'm marking my nodes in that, I can look at all the t equals f nodes, and I've got a variable field r, which says what is the enclosing function that encloses your function, right? And I can use that to rebuild a new subtree only containing those pieces, right? And I want to actually use the I, so we'll use the I over the R. I gets on this. And that gives me the same thing, but now I can get the type of the I as well, right? And I can take and I can produce, in this case we want to have the mask, and draw the I in this R, I gets tally T equals F. And so here's all the functions in the tree that match their structure, just with everything else removed. And you'll see that we marked the top root node and the other nodes. And so now we can simply delete. If we had more time, I could just delete these nodes, display the subtree with only those things in it, and then I can continue going, right? But I notice that I'm doing this all in the live state of the parser as we're parsing, right? So that's one of the big points, is that if I need to study the parser, this gives me a lot better access to that. And if I need to produce an error message, I have all of this power to produce an error message, to do type inference, to do all of this stuff directly in the parser. And it doesn't cost anything new in terms of the architecture, because the architecture is already designed in a layout that lets me put this stuff anywhere. If I need a new pass, a new piece recognized, I slot it in wherever I need to go. And at any time I make a change, the only things that will be affected by that change is code below it. So everything above it, I can easily and trivially ignore. So, all right, let's see, that's time. So, all right. Yes?
I was wondering if you compare this to the conducive parsing algorithm.
The which one?
CYK Clark. Conducive which is a bottom-up.
I think, if I remember right, that parsing algorithm is still defined in terms of BNF.
It is, but you can do things to it.
I think the difference is it's more of an architecture than it is an algorithm. It's specifically a way of making things visible and workable versus a specific algorithm for how you do the parsing. So if you wanted to do top-down with this, you could, or if you wanted to go bottom-up, you could. You could use the same architecture to do either one.